In this third video, we're going to look at the volumes of gases in a chemical reaction. So we're not going to be just looking at the measurements of one gas in terms of pressure, volume, and temperature, but we'll look at several gases in terms of their pressure, volume, and temperature as they're involved in a chemical reaction. So we're going to talk about Gay-Lussac's law of combining volumes of gases. And here's basically what it says. If the gases within a reaction are at the same pressure and temperature, then the volumes of all of the gases that are products and all the gases that are reactants are in whole number ratios. Now that's a big deal because basically what they're saying is it's exactly the same as mole ratios. The coefficients tell us volume ratios, just like we used mole ratios in chapter 9. So we can do a volume to volume problem in a reaction just like we did a mole to mole problem in a reaction. The big deal is though, both gases have to be the same temperature and pressure. If they're not, we got a whole other situation. So this is good. If we have a chemical reaction where they tell us the volume of one gas and they want us to find the volume of another gas involved in the reaction, it's simply B over A. Okay? So something that we've used before. That's good. Nice and easy calculation. Nice and easy situation. So just to give you an example here. Here's a reaction involving propane gas. This is what the reaction that happens in your house a lot during the winter. You have propane, whether it's a propane tank or natural gas coming from a gas line. It reacts with oxygen in your furnace, produces a lot of heat, but then it also produces carbon dioxide and water. Now let's just say that the propane, the oxygen, everything's at the same temperature and pressure. So we have a simple calculation here. If we have 0.35 liters of propane gas, how much oxygen will react with that propane? Also, how much carbon dioxide would be produced from that propane? Right? So just like a calculation, you got 5 grams of a chemical, how many grams of the product? Well, now we're just talking about volumes. And since we're saying in the question, they're the same temperature and pressure, how do you know? I gotta tell you in the question. We can simply set up an A to B problem. And as you see here, the two examples, you can see how the calculation would work. 0.35 liters of propane would make a significantly larger amount of oxygen and carbon dioxide. Okay. Again, we simply are just using B over A. 5 over 1 and 3 over 1. Okay. Not that big of a deal. It's nice and convenient that we can do that. All right, so one little show me I want you to do here. Let's assume that we had 2.5 liters of oxygen. How much CO2 would be produced in milliliters? Okay. So I want you to do that as a show me. It should take you just a few seconds to set that one up. Again, as we're doing these, set up the calculation, show your work. Next thing, Avogadro's Law. Avogadro's Law is something we didn't talk about in section 3, but it is another law that's very important. Avogadro's Law relates volume and moles, okay, or amount of air. Real simple one. Take a balloon, blow it up. The balloon gets bigger. Why does the balloon get bigger? Because the balloon increases its volume because the amount of air increases. Right? You put more air in the balloon gets bigger. Plain and simple. So what do we have here? We have a direct proportion. As one goes up, the other goes up. As one goes down, the other goes down. So again, we see this relationship here. V over N is equal to K. K is a constant, can't change. If the number of moles go up, the volume's got to go up. Number of moles go down, volume goes down. You open up the balloon, let some air out, gets smaller. Again, we're making the assumption here that we're not changing pressure and temperature, just to keep things nice and simple. This can be a little important piece of information as we go through some other calculations. Next little new thing that we're going to use, something called molar volume. Now, molar volume is going to be an important thing to use here. It is actually a new conversion factor. Now, it's not anything too difficult. If we just think about it here, molar volume, the volume for 1 mole. Now, this is very unique. This only works at STP. So when a gas is at standard temperature and pressure, which again is defined as 0 degrees Celsius and 1 atm, all gases, no matter what, have the same molar volume. The key is here, it's all gases as long as they're at STP. So this is good. You know, we look up molar mass on the periodic table. That tells us the number of grams that are in 1 mole. And this is different for every element. Okay? All elements are different. Here's what's nice. All gases are the same as long as it's at STP. So this is a good conversion factor to use. If we have this conversion factor, then we can solve a lot of new problems that we couldn't before. Okay? Because again, as temperatures change, as pressures change, gases are affected by that. So we need to be able to have something that can make that connection. All right. So that being said, you should be able to, on page 381, sample problem G, be able to look through how they've set that one up. And you should be able to work through a couple practice problems here for the show me. Practice problems 1 and 2. And they set up just some other examples on page 382. Sample problem H. And again, a couple other show me's, 1 and 3. Again, as you go through these, just kind of using these new conversion factors, whether that's knowing that coefficients can give us volume ratios, just like mole ratios, or realizing we now have this new conversion factor called molar volume, which relates volume in moles, just like molar mass. Okay, again, but we can't use it all the time. We can only use it when it's at STP.